And today he will talk about stability of fibrations through geodesic analysis. Thank you for accepting this invitation, Michael.
Great. Thank you very much for inviting me and for the introduction. So today what I'm going to be talking about is a sort of circle ideas in geometry where you have a geometric object, say a vector bundle or a variety, and you want to look for a canonical geometric structure on that object. So for a vector bundle, this could be a Hermite Einstein connection, or for a variety, it could be a constant scalar curvature Kähler metric. And it turns out that the existence of such a nice structure is linked deeply with algebraic geometry and in particular stability conditions. So there are two famous examples of this. One of them is a theorem and the other is a conjecture. So the big theorem is the Kobayashi Hitchin correspondence for vector bundles. But today what I'll be talking more about is the sort of Yaotian-Donaldson side, which is for constant scalar curvature metrics on varieties. And what I really want to do in the end is show how you can formulate an analogous conjecture for certain kinds of fibrations. So in particular, these are holomorphic fibrations whose fibres are compact Kähler manifolds that admit constant scalar curvature Kähler metrics. So that's this abbreviation CSCK. So yeah, so that's what I'd like to do today. So the main result that I want to present is that if you have a fibration that admits an optimal metric or an optimal geometric structure, then that is the fibration is polystable in a suitable sense that I will define and write down. And the main tool that we use to prove this is an analysis of geodesics in the space of all metrics. And in particular, you have a certain log norm functional on the space of metrics, which is convex along geodesics. Okay, so to start with, I'm just going to go through some basic background in Kähler geometry, particular CSCK metrics and K-stability. This is just a fixed notation and give a review. And then I want to talk about what the conjecture is for fibrations. So this was conjectured by Dervan and Sektnan. They sort of did all the formulation of this theory and came up with the correct definitions. And then I'll show how geodesics and convexity are sort of used to prove stability of fibrations or varieties in either setting. And then I'll hopefully have time to go through the applications. But we'll see. I'll try to keep things short. So I'll possibly end up skipping over a couple of slides just to keep things clean. Okay, so yeah, I'll just start by briefly talking about Kähler metrics. So let's let X omega be a compact Kähler manifold. So X is a compact complex manifold. Omega is a real closed positive 1-1 form. This has a Kähler class. So omega is a closed 2 form, so it has a Dervan cohomology class called the Kähler class. And if we have any other metric in the same cohomology class, then by the DD bar lemma, this differs from the original metric by a smooth function phi. So we have omega prime is omega plus I delta bar of phi. And this function is unique up to constants. And I'll write curly h for the set of Kähler potentials. So these are just the smooth functions phi on the manifold, such that omega plus I delta bar of phi is a Kähler metric. So that's what this positivity signifies. And the question that we'd like to ask is, given a Kähler class, is there a canonical or best possible Kähler metric in that Kähler class? And what Calabi taught us is that the best metric to look for is usually a constant scalar curvature metric. So what is the scalar curvature? So if we have a Kähler metric omega, we first define its Ricci curvature in the following way. So this log omega to the n is really shorthand. You just choose some local holomorphic coordinates and take the determinant of the metric in those coordinates, and then you take the logarithm. But the Ricci curvature is a real closed 1-1 form on the Kähler manifold, defined in this way. And to get the scalar curvature, we simply contract the Ricci curvature with the original metric itself. So we take the trace of this 1-1 form with our metric omega. And we say a Kähler metric is constant scalar curvature Kähler if its scalar curvature is a constant function on the manifold. And so yeah, it's a natural question to ask whether these kinds of metrics exist in a given Kähler class. And one particularly important example of a Kähler class is the first Chern class of an ample line bundle. So in this case, if you have an ample line bundle, X will be a projective smooth variety. And a canonical example of a CSCK metric is a Fubini-Studi metric. So say we have a Hermitian vector space, we can take its projectivization, and this, the Hermitian metric on V gives you canonically a Fubini-Studi metric on this projectivization. And this is in the first Chern class of the ample line bundle O of 1. So this is in fact more than CSCK, it's Kähler Einstein. But yeah, this is the sort of important example to keep in mind if you want something to refer to. So that's the sort of differential geometry side. Now, conjecturally, if we are looking for a CSCK metric in the first Chern class of an ample line bundle, this should be equivalent to a condition in algebraic geometry satisfied by this variety called K polystability. So what K polystability is, like I said, it's an algebraic geometry condition, and it's defined in terms of things called test configurations of the variety. So what a test configuration is, you basically take your polarized variety and you let it degenerate to another variety, C star equivariantly. So what that means in maths is we have a pair curly X, curly L. So curly X is a variety, and it has a projective morphism down to the complex plane. And this should be C star equivariant. And we also have a C star equivariant relatively ample line bundle on this curly X. And we want the fiber over 1 to be isomorphic to our original variety and our original line bundle, at least to some power. And of course, this means that over C star, everything will be isomorphic to this because our family is C star equivariant. But yeah, we're sort of degenerating our variety using a C star action in a sense. So that's what a test configuration is. And to define K-stability, we use the Donaldson-Futaki invariant of a test configuration. So perhaps the easiest way to define this is we see that over the non-zero complex numbers, our test configuration is really trivial in a sense, because we can use the C star action to trivialize it, because everything is C star equivariant. And once we've done that, we can sort of extend things trivially over infinity, sitting in P1. And then what we get is we get a test configuration really living over P1. And this is going to be a complete or compact variety. And to define this Donaldson-Futaki invariant, we just take some intersection numbers. So here n is the dimension of our original variety. Mu is the slope of the variety. It's just essentially a topological constant. And we've taken some intersection numbers over x bar, which is our compactified test configuration. So yeah, we're assuming that everything is normal here so that we can actually define these intersection numbers. And here, in particular, this relative canonical bundle is really a Weil divisor. So that's test configurations and the Donaldson-Futaki invariant. So we say that our variety is K semi-stable if the Donaldson-Futaki invariant is always non-negative for any test configuration. And it's K polystable if it's K semi-stable and whenever the Donaldson-Futaki invariant is 0. Our test configuration is what we call a product test configuration. So that means it's isomorphic to just our original manifold product with the complex plane, and we pull back the line bundle from X. And we don't require the C star action on this to be trivial. We're actually allowed to have a non-trivial C star action, and that's important. So yeah, this is K stability. And conjecturally, K polystability is equivalent to existence of a CSCK metric. So that was the sort of a story for Kähler manifolds and K-stability. So now I want to give sort of analogous theory for the fibration setting. And before I do that, what I need to do is I need to introduce something called holomorphy potentials. So this is just a technical notion that will come up throughout the rest of the talk, but it's not a sort of standard thing. So I thought I should go through it a bit carefully. So what a holomorphy potential is, it's a smooth function on your Kähler manifold such that it satisfies this equation. So this curly D takes del bar of the 1, 0 component of the gradient of f, and we want this to be equal to 0. So what this is saying is that we take our gradient of our function, we take its 1, 0 component, and we're asking that this be a holomorphic vector field. So the reason we care about holomorphy potentials is because they give us ways of generating biholomorphisms of our manifold. So if we flow along this holomorphic vector field, then we sort of get a one parameter group of biholomorphisms of our manifold. So the space of all holomorphy potentials is finite dimensional, and I'll write in particular E for the space of holomorphy potentials that have integral 0. So of course the constant functions will all be holomorphy potentials, but we don't care about those because they're going to generate the trivial holomorphic vector field when we take the gradient. Okay, so the reason we care about these holomorphy potentials is because they tell us how to infinitesimally deform constant scalar curvature Kähler metrics. So suppose that we do have a CSCK metric. It turns out the space of all CSCK metrics in the same Kähler class is a negatively curved symmetric space. So it's this G mod K here, where G is the automorphism group of our manifold X, and K is the isometry group of our metric. So K is actually a maximal compact subgroup. So that gives us that this is and the automorphism group is reductive as well. So that gives us that this is a negatively curved symmetric space, and it's contractible, in fact. And the reason why we care about holomorphy potentials, the tangent space to any CSCK metric is the space of integral 0 holomorphy potentials. Okay, so given a holomorphy potential, we can sort of generate deformations of our CSCK metric. Okay, so that was just a bit of technicality. So now I can finally talk about the fibration setting and what we're interested in this setting. So the objects that we're looking at are fibrations x, h over bl. So here, x and b are compact complex manifolds. This map pi is a holomorphic surjective submersion. So it actually has nothing to do with x and h and l. We just want to map from x to b. We have an ample line bundle, L over the base, and a relatively ample line bundle on X. So whenever I write down this data, I'll mean all of this. So X is living over B, we have an ample line bundle on the base, and a relatively ample line bundle on the total space. We'll also make 2 additional assumptions. So first of all, every fiber, X little b, will admit a constant scalar curvature Kähler metric in the class of our relatively ample line bundle. Okay, so this is a reasonably strong assumption, but it's an important one to make for what we're going to do. So wherever you see little b, that just means a point in the base, big B, and we'll be looking at the fiber over that point. And the other technical assumption we need to make is that the dimension of the automorphism group, or of the space of holomorphic vector fields on each fiber, does not vary with the base point. So in particular, if all the fibers are isomorphic as complex manifolds, then this second assumption will be satisfied automatically. So these are the kind of objects that we're interested in, and we want to have a notion of a sort of metric on this object. And what we do, so if we make all of these assumptions, then what we can show is that there's actually a real closed 1-1 form, omega x in the first germ class of our relative bundle, H, that restricts to a CSCK metric on each fiber. So I'll write that as omega little b on the fiber x little b. And all omega x a relatively CSK metric. Okay, so this is the kind of it's the analog of Kähler metric that we want to study. So we want to essentially look for a canonical kind of metric of this form. And this is all quite abstract. So what I want you to do is keep in mind the following example. So suppose we have a Hermitian vector bundle on our base. Then what we can do is projectivize it. And then we'll be in this situation here. So we'll have the projectivized vector bundle living over it'll be a holomorphic surjective submersion. On the base, we assume we have an ample line bundle, and then the relative O of one line bundle will be H, so that'll be relatively ample. But on each fiber, the metric, the Hermitian metric H, gives you a Fubini-Studi metric on each fiber. So what we have is we get a closed 1-1 form on this projectivized vector bundle that restricts to a Fubini-Studi metric on each fiber, and that's CSCK on every fiber. And it's easy to see from this example that there are sort of lots of these things. So we know that there are loads of Hermitian metrics on a vector bundle. So that means we can produce loads of these relatively CSCK metrics, the fibrewise Fubini-Studi metrics. So that's the sort of, yes?
Do you require B to be compact? All of these doesn't seem to require B to become compact.
Yeah, so the definitions make sense when B is not compact, but when I'm going to show stability, I'll need B to be compact. So for all the results that we're going to prove, we need B to be compact, but yes, you can make these definitions simply for B non-compact as well.
Okay.
Yeah, thank you. So yeah, so that's relatively CSCK metrics. These are the objects that we want to look at. And just as for Kähler metrics, we had Kähler potentials. For the relatively CSCK metrics, we also have potentials. So I'll write this space as K sub E. The reason for E will become apparent. But yeah, this is simply the smooth functions on our total space of our fibration, such that if we add I delta bar of that function, then we get another relatively CSCK metric. So assuming we have one of these metrics, we get an L2 inner product on the smooth functions on our total space. So yeah, so I should have written, we assume we fix a Kähler form B on the omega B on the base, and we pull it back to our total space. So that's what this here is denoting. N is the dimension of the base, and M is the dimension of the fiber. And because our relatively CSCK form is Kähler on the fibers, this will be a positive volume form. So we have this positive volume form, and we can take inner products of functions. And that gives us an orthogonal L2 decomposition of the smooth functions on X. So first of all, you have smooth functions pulled back from the base manifold to the total space. And then you have everything that's left over. So these two spaces add up to functions that have integral 0 on the fibers. But what C infinity E denotes, these are the functions on the total space that restrict to a holomorphy potential on each fiber. So F is in C infinity E, if and only if its restriction to every fiber is a holomorphy potential with integral 0. So remember, this means the 1-0 gradient of the function F is a holomorphic vector field. So F generates a holomorphic vector field. And R is just simply everything else that's left over. So the important things that we care about are C infinity B and C infinity E. And that's essentially because of the following thing. So if we want to deform a relatively CSCK metric, we do that essentially by taking something in the first two components. So Dervan and Sektnan show that if you have a smooth path in the space K sub E of the relatively CSCK potentials, then its derivative lies in these two spaces. So this is really the tangent space to this infinite dimensional manifold. Okay, so the C infinity E, this is deforming our CSCK metrics on the fibers, because we know that holomorphy potentials are the deformations of CSCK metrics. And the C infinity B component, this is just deforming our metric in the horizontal directions, which is kind of irrelevant. You can essentially ignore the C infinity B component, or think of it as the analog of constant functions in the non-relative setting. But yeah, so that's CSCK potentials. And what we want to do is find a sort of canonical choice of a relatively CSCK metric. So this will be the analog of CSCK in the varieties case, or Hermite Einstein in the vector bundles case. So yeah, I should have said this earlier. We fix a base metric in the first Chern class of L, omega B. And what we do is we pull it back to our total space and we add larger and larger multiples of it. So we're taking a sort of large volume limit, or an adiabatic limit, where the volume of the base goes to infinity. And because omega x is positive in the vertical directions, omega b is positive in the horizontal directions, if we take k large enough, then we get a Kähler metric on our total space. And here's the theorem. So if we expand the scalar curvature of this metric omega k, plus a slight deformation, we get the following. So this leading order term is the scalar curvature of any of the fibers. And this is actually a topological constant. So this leading order term is actually constant over the entire total space. We get this subleading order term as well, which is the scalar curvature of the base, plus something that I'm writing P of theta. And this P of theta is actually what we're going to define our optimal symplectic connection equation by, our notion of optimal metric. Okay, so P is denoting the orthogonal projection to the fibrewise holomorphy potentials, and theta is a certain function that I won't explain what it is because it's not entirely important. But yeah, so the point is that if P of theta is 0, okay, I'm simplifying here, but suppose that our scalar curvature of the base is constant and P of theta is 0, then what this allows us to do is it allows us to perturb this sort of large volume metric to a genuine constant scalar curvature metric on the total space. So we call a relatively CSCK metric an optimal symplectic connection if it satisfies this equation P of theta equal to 0. Okay, so yeah, so I haven't really defined what the equation is because I haven't defined all of these terms. I'm just saying that it arises when you're trying to construct a constant scalar curvature Kähler metric on your total space. And the way that that works is you take this expansion in the large volume limit on the base. And in order to perturb to a CSCK metric, you need this P of theta term to vanish. Okay.
So this is may I ask the question here?
Mm-hmm.
Just to be sure that I understand. So let's take one very simple example. For instance, a principal torus bundle.
Sure.
And then just some variety that has this torus in the automorphism group and form the fibration. Sure, in this case, this theta will be automatically 0, what you say, and if the base is constant scalar curvature, in the fiber is constant scalar curvature, you can cook up.
Yeah, exactly. So if you can find a relatively CSCK metric satisfying this condition, yeah. So P of theta is 0, then you can cook up a CSCK metric on the total space.
And if you have a principal torus bundle or some sort of Hermite Einstein condition,
exactly.
This
yes.
will be
yeah.
Okay.
Yeah. So one example, if you have a vector bundle with a Hermite Einstein metric, and you projectivize the bundle, that gives you a relatively CSCK metric, and that satisfies this condition, P of theta equal to 0. So that gives you an optimal symplectic connection, and it allows you to construct a CSCK metric on the total space. So this was a result by Hong from a while ago, and this condition P of theta being 0 is generalizing that essentially. So yeah.
I have a question about that result because yes, you Hong construct them in case Futaki's invariant is 0 as well, and that may never happen. So is that extremal metrics you are looking for, or really constant?
Yeah. So really, I'm kind of fudging this result. So there should be assumptions on the automorphism groups.
Oh, okay.
So the automorphism groups should be finite. Yeah.
Oh.
Yeah, I just wanted to sort of simplify things, but you've caught me out. Yeah. Thank you. Okay, so that's the notion of metric that we're looking at. The notion of stability is the following. So we look at fibration degenerations. So this is similar to a test configuration. So what we do is we take a curly x, curly h, and this is a normal variety curly x together with a projective morphism, not just down to the complex numbers, but also down to the original base b. And we want this to be flat over the complex numbers. We want it to have connected fibers and C star equivariant. Okay, so now instead of looking at a sort of C star degeneration of our variety, we're looking at a C star degeneration of the fibration as a whole, in fact. So that's what this is saying. And we want it to be flat over the complex numbers, but not necessarily over B. We also want a C star equivariant line bundle that's relatively ample over the base. And we want the general fiber to be isomorphic to our original fibration. So we should have an isomorphism of the fiber over 1 with our original thing, but this isomorphism should be over the base B. Okay, so it's very similar to the definition of a test configuration. But what you should keep in mind is the following example in the vector bundles case. So say we take a coherent subsheaf of our holomorphic vector bundle, then we can degenerate our vector bundle to that coherent direct sum with its quotient. So there's a family of vector bundles over the complex plane such that the central fiber is this vector bundle and the general fiber is our original vector bundle B. And if we take the projectivization of this, then we get a fibration degeneration of P of V to this other projected bundle. Okay, so this is the kind of example to keep in mind. So that's fibration degenerations. So remember, for test configurations, we needed the Donaldson-Futaki invariant to define stability. So here, to define our invariant, in this case, what we do is we simply expand the Donaldson-Futaki invariant. So if we pull back a large multiple of the base line bundle and add it to curly h, then we get an ample line bundle on our test configuration or in our fibration degeneration, but then that is a test configuration for the total space. So we can take its Donaldson-Futaki invariant and we expand that in K as K goes to infinity. And we get these constant terms W0 and W1 plus some lower order things. So to define stability, we say our fibration is, first of all, semi-stable if this W0 invariant is always non-negative. And whenever it's equal to 0, we have that this W1 invariant is, again, non-negative. So we're looking for the first two terms in this expansion to be non-negative. And it's polystable if it's semi-stable. And whenever you have these invariants both equal to 0, the fibration degeneration really comes from a product degeneration. So it's isomorphic to x times the complex numbers like before. Okay, so those are our definitions of stability. And just one quick result to understand these fibration degenerations. Dervan and Sektnan show that for a general point in the base, the W0 term is actually the Donaldson-Futaki invariant of the fiber over that point. So for each point in our base, we actually have a test configuration of the fiber, and W0 will be the Donaldson-Futaki invariant of the general test configuration. But if our fibers are CSCK, like we're assuming, then they're all K polystable. So all of these fibers are K polystable, and therefore this Donaldson-Futaki invariant is non-negative. So it's actually automatic that W0 is non-negative in this definition of semi-stability. And if W0 is equal to 0, that means the general fiber actually normalizes to a product configuration. Okay, so in this example of the degeneration of a vector bundle, W is a coherent subsheaf, but generically it's a vector subbundle. So over a dense open subset, W is a vector subbundle of V. And when we projectivize this degeneration, wherever W is a vector bundle, we're going to get a product test configuration, because the central fiber will just be another projective space. So that's how you can see explicitly in this example that most of the fibers are going to be product configurations. Okay. So that's optimal symplectic connections and stability of fibrations. The main conjecture is that these two are equivalent. So Dervan and Sektnan came up with this conjecture that a fibration admits an optimal symplectic connection if and only if it's polystable. And we have some results towards this. So first of all is a result by Dervan and Sektnan. So if the fibration admits an optimal symplectic connection, then it's in fact semi-stable. And what I've shown is that if the fibration admits an optimal symplectic connection, then you can in fact improve semi-stability to polystability for a large class of fibration degenerations. And the ones that you can do this for are the ones whose fibers are all product test configurations. Okay, so we know that generically, most of the fibers on a fibration degeneration are going to be product configurations. So this result applies when all of the fibers are product configurations. And in the case of vector bundles, this is essentially assuming that we're looking at a vector subbundle of our vector bundle rather than just a coherent subsheaf. So that's what this result is kind of giving an analog of. Okay, so yeah, that's the sort of setup and the main conjecture that we'd like to look at. So now I want to talk about the tools for how we actually prove this. So I guess I have 15 minutes and I'm only really halfway through the talk, so I'll probably have to skip over some things. But yeah, so the way we study stability is through geodesics. So I'll talk about what that means in the Kähler case first. So recall we have a compact Kähler manifold and the space of Kähler potentials on that. We want to define what it means to be a geodesic path in this space. So if we have any smooth path in the space of Kähler potentials, we can write down the energy of that path. And this is essentially exactly what you would do in finite dimensional Riemannian geometry. You just take the sort of L2 norm of the tangent vector and you integrate that. And a geodesic is by definition a critical point for this functional. And by taking the Euler-Lagrange equation of the functional, you can show that a smooth path is a geodesic if and only if it satisfies this equation. So the second t derivative is the norm squared of del of the first t derivative. So yeah, in finite dimensions, you look at the geodesic equation and you get an ordinary differential equation. But because we're looking at smooth paths in an infinite dimensional space, we end up with a PDE as our Euler-Lagrange equation. So this is what it means to be a geodesic in the space of Kähler potentials. So geodesics, they always exist, but only in a weak sense. So if I have any 2 points in the space of Kähler potentials, I can join them by a unique geodesic, but it might not be smooth. So we can only ask for a C11 regular geodesic. And the geodesic equation, this is just a comment, it's equivalent to what we call a degenerate Monge-Ampere equation. And a really important class of geodesics is given by holomorphic vector fields, or if you like, holomorphy potentials, because we know they generate holomorphic vector fields. Okay, so say we have a holomorphic vector field, we can take its flow, and this is flowing sort of by biholomorphisms of our complex manifold. And we can sort of pull back the metric by the flow. So we let the metric evolve along the flow. And because this will be cohomologous to our original metric by the DD bar lemma, we can write it in this form. And if we normalize these functions phi t suitably, then we end up with a geodesic. Okay, so this tells us that if we flow along the automorphisms generated by a holomorphic vector field, we get a geodesic. And if our holomorphic potential is non-zero, then we generate a non-trivial geodesic in the space of Kähler metrics. Okay, so that's a bit about geodesics. So how do we actually use them? Well, we analyze what we call the Mabuchi functional. So this is a functional defined on the space of Kähler potentials. And its first variation is given, it's defined through its first variation, which is this. So we want to take the inner product of our sort of tangent derivative with the scalar curvature minus its average. So here phi t is a smooth path in the space of Kähler potentials, and we also normalize it so that it's zero at the origin. So this functional is called the Mabuchi functional, and what you'll notice is that the critical points are exactly the constant scalar curvature Kähler metrics. So this is the first variation. When does this variation vanish? It vanishes only if this term here vanishes. So S hat, which is the average scalar curvature, is equal to the scalar curvature, but that means your scalar curvature is constant. Okay, so we have this functional whose critical points are precisely the CSCK metrics. If you look at the second variation of this functional, you get the following. So you notice the geodesic equation from the last slide appears here. So if we're looking at the second variation along a geodesic, this vanishes, but this term here is non-negative. So what that means is this functional is convex along geodesics. Okay, and it's in fact strictly convex. So this term, for this term to vanish, that means that your geodesic is actually arising from a holomorphic potential. So we have strict convexity unless we're looking at one of these geodesics generated by a holomorphic vector field. Okay, so yeah, so there are a couple of very important applications of this. First of all is uniqueness of CSCK metrics. So if we have two CSCK metrics in the same Kähler class, then they're related by a holomorphic automorphism in the identity component. So I wrote down the proof for this, but due to lack of time, I'll just skip over it. And the second application, I didn't quote this one. This is by Berman, Darvash, and Blue. This says that if we have a CSCK manifold, then it's K-polystable. So both of these use convexity of the Mabuchi functional along geodesics. Okay, so that's the kind of geodesic story we have. We're looking at the space of all metrics, and we want to ask what it means to be a geodesic in that space. And we have a functional which is convex along geodesics. So this is the picture that I want to have in the fibration setting. So let's go back to the fibration setting. So I've got X over B with a relatively CSCK metric, and I've got the space of relatively CSCK potentials. And just as in the Kähler case, I can write down a natural energy functional on smooth paths. It's just exactly what you would expect. And I say that a geodesic is a critical point for this functional. And taking the first variation of this functional, you can prove the following. So a smooth path is a geodesic if and only if it satisfies this equation. Now, what you'll notice about this equation, so here V, this curly V, this means vertical. So what I do is I restrict everything to a fiber. I do the del operator on that fiber, and then I take the vertical norm of that. Okay, so I'm doing everything fiberwise. But what that means is this is just the normal Kähler geodesic equation, but on each fiber. So I just have the standard geodesic equation, but fiberwise. And what you can prove actually is that if we have two CSCK potentials, there's a unique smooth geodesic joining them. So this might be somewhat unexpected because we know that in the Kähler setting, we only have weak geodesics between metrics. The reason we get smooth geodesics is because on each fiber we have a CSCK metric. And the geodesics between CSCK metrics, they're generated by these holomorphic vector fields or holomorphy potentials, and those are automatically smooth. Okay, so on each fiber we have a smooth geodesic, and the way that we show that we can find a unique smooth geodesic is just by piecing these together, and they're pieced together smoothly. Okay, so yeah, this is essentially what I'm explaining on this slide. So yeah, we get existence and uniqueness of smooth geodesics. And the proof actually gives you a Riemannian splitting of the space of relatively CSCK potentials. So here G mod K, this is a fiber bundle whose fiber over a point is the space of CSCK metrics on that fiber. So it's a fiber bundle whose fibers are homogeneous negatively curved spaces. And we get a splitting that integrates the tangent space decomposition that we saw earlier. So we get the smooth functions of B. This actually turns out to be a flat piece of this, and we get the sort of fibrewise CSCK metrics. So yeah, this is a Riemannian decomposition. The smooth functions on the base are a flat submanifold, and we have these fibrewise CSCK metrics being non-positively curved. So this C infinity G mod K, it's essentially forgetting the horizontal data, and we're just remembering what each fibrewise CSCK metric is. Okay, so that's geodesics. The log norm functional, it's defined exactly as the Mabuchi functional is defined, except instead of the constant scalar curvature equation, we insert our optimal symplectic connection equation. Okay, so this is defined so that this functional n is defined so that its first variation is given by the optimal symplectic connection operator. And yes, so just as before, the critical points of this functional are exactly the optimal symplectic connections. So just as for the Mabuchi functional, you can show that this functional n is convex along smooth geodesics, and it's strictly convex unless your geodesic arises from a vertical holomorphic vector field. So for the Mabuchi functional, we knew that it was convex and strictly convex unless our geodesic arose from a holomorphic vector field. Here we have to take a vertical vector field, a vertical holomorphic vector field. And the reason is because these are what generate the automorphisms of our fibration. So an automorphism of our fibration is simply a biholomorphism of the total space that preserves all of the fibers. So you can write that as, if you take the projection, then it doesn't remember the automorphism. Yeah, and so this is a complex Lie group, and its Lie algebra is simply the vertical holomorphic vector fields. So we have strict convexity of our log norm functional, unless our geodesic comes from a vertical holomorphic vector field. And to prove this, you take its second variation of this functional, and that involves this operator here. So if we have a fibrewise holomorphy potential, we can take its vertical gradient, and that'll give us a holomorphic vector field on each fiber. But these holomorphic vector fields only glue to a smooth vector field. And it's globally holomorphic if and only if del bar of that is 0. So this operator R, it's telling us whether a smooth function that's fibrewise holomorphy potential is generating a vertical holomorphic vector field. So that's what this operator R does. And it turns out if you compute the second derivative for this functional n, you get the geodesic equation appearing here, plus this non-negative term. So if we're moving along a geodesic, this term vanishes and we have convexity. And it's strict convexity, again, unless we are sort of moving along one of these trivial geodesics that comes from a vertical vector field. And that's what I'm just saying there. Okay. So yeah, I'm getting close to the end. So one application of this is uniqueness, but I'll skip over that because what I really want to talk about is stability. So yeah, so you can prove uniqueness of optimal symplectic connections using this convexity, but also you can prove polystability, that result that I stated. So let's say we take fibration degeneration of our fibration such that every fiber is a product test configuration. Okay, so this was the assumption that I needed in the theorem. What we do, the strategy, is to associate a smooth geodesic ray to this fibration degeneration. And there's a little footnote here of explaining how you do that. Really, you consider your geodesic ray, you transform it so that it's a function on the punctured disk across your manifold, and then you want that to extend smoothly over your fibration degeneration. But yeah, we're essentially using our fibration degeneration to construct a geodesic ray. And once again, we do this fibrewise and show that the fibrewise geodesic rays glue smoothly to a globally defined geodesic ray. And what you want to show is that the limiting slope of this log norm functional is actually the W1 invariant. So this W1, you'll recall that it is determining stability. So because all the fibers are product test configurations, we know that W0 is 0, or we can assume that. And what we want to calculate is this W1 invariant. Now, because n is convex along geodesics, its limiting slope will be non-negative. And it'll be strictly positive unless our geodesic is one of these trivial geodesics. So this is essentially how we prove polystability. It's how we show this W1 is non-negative. And to calculate this limit, what you do is you prove an analog of the Chen-Tian formula for the Mabuchi functional. So this is the usual Chen-Tian formula for the standard Mabuchi functional. It's this complicated looking thing. But the point is, these terms each correspond to an intersection number that appears in the Donaldson-Futaki invariant. So each of these terms really corresponds to an intersection number, and you can kind of show that as you go along a geodesic, the Mabuchi functional returns the Donaldson-Futaki invariant. But yeah, so the strategy to prove a Chen-Tian formula for my functional n is to expand the usual Mabuchi functional. So Dervan and Sektnan show that the functional n that we're interested in is really the subleading order term in an expansion of the Mabuchi functional. Okay, so to prove a Chen-Tian formula, all you have to do is expand this thing, which is easier said than done. But once you do that, you get this big ugly formula for the functional n. And once again, all of these terms correspond to intersection numbers. And you use this kind of correspondence with intersection numbers to show that the limiting slope of your functional is the invariant W1. So yeah, so I won't go through what all of these are, but yeah, I'm essentially out of time now, but I'll just quickly say sort of what the general idea is. To prove that these terms give you intersection numbers, you use Deligne pairings. So this is some general machinery that, say, for example, lets you write write a difference of metrics in terms of these expressions appearing in the Chen-Tian formula. And there's a theorem by Buxom, Hisimoto, and Jonsson that tells you that if you take a difference of these Deligne pairings, then you essentially get an intersection number as your leading order term. Okay. So because W1 can be defined in terms of intersection numbers, for instance, this is one of the intersection numbers appearing in W1. We can just apply this theory of Deligne pairings and get that in the asymptotic limit, we recover the intersection numbers. So yeah, so that's how you prove this. So you notice when you divide out by t, you just get this intersection number plus some lower order stuff that will vanish as you go to infinity. Okay. So yeah, so that was all a bit rushed near the end, but we got there. So that's how you prove polystability. All right, so thank you very much for listening.
Thank you, Michael. I mean, there's a little surprise in or what you said is the appearance of this smooth geodesics. So, yes. So can you come back a bit to this and explain to us a little bit more in details, because that's a surprise.
Yeah. So even though it's a geodesic equation in the Kähler setting on each fiber, what you should really be thinking about is vector bundles. So we know in the vector bundle setting, we have these smooth geodesics between any two Hermitian metrics. So say we're looking at a projectivized vector bundle. That means that the geodesics between Fubini-Studi metrics, fibrewise Fubini-Studi metrics, will also be smooth. So the reason we get these smooth geodesics is really from the fibrewise CSCK assumption. So we have this finite dimensional homogeneous space, G mod K, parameterizing the CSCK metrics. And the geodesics in this case, in this space, are all smooth. So on each fiber, we have a smooth geodesic, a unique smooth geodesic, and you can show that they do vary smoothly. And the way that you do this is you essentially show that this fiber bundle, whose fiber is this homogeneous space, embeds into an infinite dimensional Frechet bundle, whose fibers are the fibrewise Kähler potentials. But yeah, so once you have a smooth section of that Frechet bundle that happens to lie in G mod K, well, that means it's a smooth section of G mod K, and then it's trivial that the geodesics are sort of smooth in that space because it's a finite dimensional space. So yeah, this is, so really the geodesic equation is in some sense an ODE because the geodesics in this finite dimensional space are ODEs. But yeah, so this is why we get smooth geodesics. It's also why I have to assume that all of these, so when I'm proving polystability, I assume that all the fibers are product test configurations. That's also so that I get smooth geodesics. Because you can show explicitly in that case that the geodesics have to be smooth.
And I have another question also, I mean, and then that I will let the other participants to ask questions, I'm sure there would be. Is what can you say in the case that the base is a curve? I mean, are there like some more specific results in this particular case?
Yeah, so nothing yet. I was thinking about this a bit though, and it should, you know, morally be easier to, I was hoping that there would sort of be a full proof of polystability in the curves case. It should be doable, but definitely non-trivial. So you would hope that you could reduce to this result here, that allows you to consider product degenerations whose fibers are all, fibration degenerations whose fibers are all product configurations. And that's sort of analogous to vector bundles over curve. Over a curve, you can just consider sub-vector bundles. You don't have to look at coherent subsheaves. There are some slight subtleties though, because you can have sort of fibers that are generically product configurations, but you can have a single fiber that is not a product configuration that normalizes to a product configuration. So it's only a small subtlety, but it does cause issues. But yeah, there should be some way of proving polystability in that case, sort of getting a full result.
Okay, very good. Are there any other comments or questions?
Yeah, I probably will have one question. So you essentially use this a priori condition that the fibers are constant scalar curvature.
Yes.
But can we think of some sort of stability condition out of not assuming a priori that the fibers are constant scalar? Let's say assuming the total space has constant scalar curvature extremometrics in these limiting classes. Can you do the same machinery to?
Yeah. So this definition actually, it works perfectly well, even assuming that the fibers aren't CSCK manifolds. So this definition of stability really works for any algebraic fibration. In order to get something sensible, you would need to assume at least that the general fiber is K semi-stable, because we know that the Donaldson-Futaki variant of the general fiber is this W0 term. So we need to look at fibrations at least with a general fiber is K semi-stable. But there's, no sort of analog of the correct notion of optimal symplectic connection on the differential geometric side yet. But yeah, morally speaking, you should be able to, go on.
Yeah, I was thinking really, for instance, in the case the fiber are just extremo, so then, you can still consider the question of existence of extremometry calorimetrics, given that the fiber is extremo. And indeed, there are examples, actually there are results which say that if the fiber is extremo and if the connection is projectively flat, for instance, or the fiber is projectively flat, then in the limiting case, you have extremometrics. So they should be generalizable in
so this
will be not
there is a notion of this sort of extremal thing. I should have said, so Dervan and Sektnan have written down what it means for one of these relatively CSCK metrics to be extremal. It's basically what you think. You take the usual relatively optimal symplectic connection equation, you take the 1, 0 gradient, and that should be 0, or the vertical 1, 0 gradient, sorry. But yeah, there is a motion, and there should conjecturally be a link between stability there. Yeah.
Okay.
Thank you.
Okay, very good. Are there any other questions now? I don't think so. So let's thank the speaker for his very nice talk.